Welcome. In this video, we're going to introduce the notion of concavity. Let f be a function that is differentiable over an open interval I. If f prime is increasing over I, we say, and I have a blank. If f prime is decreasing over I, we say f is, and again, another blank. Now, before I fill in these blanks, let's sketch some pictures. There in purple, I've sketched f with a vertex here at this point. And I'm just going to call that point, not like it matters, x. Now, the tangent line here is negative. That tells me if I want to sketch f prime, then my tangent line until x has to be below the x-axis, so somewhere around here. Next, we know right at x, the vertex, the tangent line is horizontal, so the first derivative is equal to 0. So I know my sketch of f prime will cross the x-axis right here at this point, x. Okay, finally, our tangent line has a positive slope here. So on the right side of this point, my tangent line, so my derivative of f, has to be sketched somewhere over here. So f prime is going to look something like this. If you notice, f prime is what? Is it increasing or decreasing? Am I in this case or am I in this case? If you said we're in the first case, you're correct. F prime is increasing. Now, that means we say what? Well, you can think of this as a cup that's pointing up that can hold liquid. So here's a wine glass or a funky martini glass that holds liquid. So this is concave up. And now, just to help us get into the test for concavity, let's look at the second derivative of this function. The second derivative, as we've already talked about, the first derivative has a positive slope. That means the second derivative is going to be completely above the x-axis. So f double prime would be here. And let's put a pin in this. Hold on to this concept until we get to the test for concavity lower down on this page. So next, let's explore the case where f prime is decreasing. So in that case, I know my first derivative is decreasing. So I'm going to start with a picture of my first derivative. So when f prime was increasing, it looked like it was going uphill. If f prime is decreasing, then we know it'll be going downhill. So we can sketch f prime like this. What does this tell us about our original function? Well, we know our function has a horizontal tangent line here at x. Our slope for our tangent line is positive here. So that means we are above the x-axis. So we're going in this direction. And the slope of the tangent line is negative here. That means we're going down like this because the tangents to this line would be all negative. So as you can see here, the tangent line on the left side of x is positive. The tangent line on the right side of x is negative. That corresponds to above the x-axis here and below the x-axis here. And then right at this maximum value, so right here on top, we have a horizontal tangent line. So the slope of my tangent line, or that is f prime, is 0 right here at x. So clearly our first derivative has a negative slope since the slope here is going down and right. So f prime is decreasing. So we say f is concave down. So now I'm going to take this to an additional step here, which we'll look at more for our test for concavity lower down in the page. So the slope here, as we discussed, is negative, so it's going downhill. That means my second derivative is going to be negative, so completely below the x-axis here. And that is my sketch of f prime prime. Before we discuss the test for concavity, let us make a quick note that in this case, our function f is concave up, and here f is concave down. Now let's go ahead and discuss the test for concavity. All right, so as you can see here, we have our sketches from the previous definition of concavity. And we have the sketches of the second derivative. We didn't really use these to define concavity, but we sketched them anyway, so we'd have the sketches. And now that we have the sketches, we can use them. The test for concavity, let f be a function that is twice differentiable over an interval I. If the second derivative is greater than 0 for all x on that interval, then f is what? So which one of these has a second derivative that is greater than 0? If you said this one on the left, you're correct. Our second derivative here is above the x-axis. So the second derivative of f is greater than 0. And in that case, we're concave up. Well, not us. F, the function, is concave up over the interval. Next, if our second derivative is less than 0, and that's the case here on the right, then f is concave down.